Hello, my name is Jim Blando, and I'm an associate professor at Old Dominion University in Norfolk, Virginia. Today, I'm going to discuss an overview of exposure assessment, and in particular, we're going to talk about a specific approach to conducting exposure assessments delineated by US EPA. This specific scenario approach that we're going to discuss today is a utilization of modeling to help us support an assessment of exposures for specific scenarios. So one of the key things I want to start out by pointing out is that when we utilize computer modeling, there's a lot of analogies to the approach when we actually conduct environmental sampling and monitoring. Computer models do require a clearly articulated scenario that is also documented, but there also has to be a modeling plan with data quality objectives. Just like when we go out and collect environmental samples, we have to have data quality objectives. We need the same data quality objectives when we're utilizing computer models. And those data quality objectives should be clearly listed and noted in our modeling plan. Similarly, just like when we want to utilize validated sampling methods, we also want to utilize a validated model, a model that has been assessed for its accuracy and precision and its limitations. Oftentimes, sophisticated models will be calibrated for a specific scenario, just like when we go out and collect environmental samples where we may calibrate our instruments. Oftentimes, we want to calibrate our computer model for the specific scenario we're evaluating. We, of course, want to clearly document all of this. And certainly, this is more of an editorial point on my part, but I like to utilize valid models, but also validate those models with actual environmental samples, if at all possible. But computer modeling requires all of the same quality control and quality assurance procedures that one would use, similar to if we were going out to collect samples in the field. There are many types of environmental models that exist today. The increase in computing power over recent decades has really increased the sophistication of computer models that can be utilized to model exposures in the environment. Of course, they utilize mathematical relationships to predict concentrations and exposures. Some models out there now that have been developed, especially by EPA, have incorporated detailed chemistry models that can also evaluate the fate and transport and change in chemicals as they move and exist in the environment. Typically, computer modeling continues to improve as more computing power becomes available and as people continue to develop these models further. For example, many years ago, we did some studies where we showed that secondary organic aerosols could be formed as a result of the processing of organic vapors and gases in cloud and fog droplets. That has since been incorporated into some of EPA's models and have improved the accuracy of those models in predicting secondary aerosol formation. So models continue to develop and get more powerful as time goes on. This is just an example. This equation is a three-dimensional Gaussian dispersion equation. My only point to showing you this equation is I just want to make the point that computer models are very mathematically intensive. They utilize a lot of mathematics to come up with their estimates. And if you like math, it's a great endeavor if you enjoy doing mathematics because they are mathematically intensive. But the utility of air dispersion modeling or computer models is that I can connect a source like this smokestack here off in the distance, and I can actually develop estimates over a geographic range that allows me to estimate what the pollutant concentrations would be over that geography. So that's where computer models can be very valuable because I can generate a lot of data. Once I have the computer model calibrated and the proper inputs, I can do this relatively quickly, and that can be very valuable. Of course, the key limitation is the inputs to the model are going to drive the accuracy and precision of the outputs of the model. So we always want to avoid that scenario where, garbage in, garbage out. If you have terrible input data, your model results are not going to be very good. But again, very mathematical, very useful. As I've already mentioned, some of EPA's models also can evaluate fate and transport of the compound. So not only can I evaluate, for example, the air dispersion model about where is the pollutant going in the environment, I can also evaluate how the chemicals are going to change as they move through the environment. It goes without saying there are many chemicals that when they're released to the environment, when they're exposed to sunlight, they're exposed to moisture, they can undergo chemical reactions in the environment. Sometimes there are microbes that exist in water or soil, for example, that can actually digest or metabolize chemicals that are released to the environment. So the fate of these individual chemicals and the metabolites that are produced are also important for us to assess. There are some classic examples out there. For example, some halogenated hydrocarbons, when they're in the environment for a period of time, they can actually form vinyl chlorides or other compounds. The metabolites may have a different toxicity than the original parent compound. So we need to understand not only where the pollutant is going, but also how it's transforming in the environment and what it's becoming. And nowadays, with the advances in modeling technology, some of these fate and transport models actually incorporate modules that can help the exposure assessor estimate what the metabolite exposures may be. So why are these models so helpful? Models are super helpful because they connect the pollutant source to pollutant receptors, right? So I may have emissions at one location, then I can utilize models to connect how they're transported and what they become when they're exposed to pollutant receptors, like these two cute kids in this particular picture here. So that's why models are so helpful. These models are very, very helpful because they allow me to connect the emissions to the receptor. You'll note here, there's an example YouTube video, which is a news report that shows utilization or where models can be very, very helpful. This link will be provided in the lecture notes associated with this discussion. One of the things that's important, as I mentioned already, is that when we're looking at given scenarios, it's important that we have good, valid data that we input into these models. If we don't, we could have garbage coming out, garbage in, garbage out. So we want to avoid that situation when we're modeling a given scenario. So when we look at the data needs, it's important for us to have valid data to input into the models. US EPA in particular has put a lot of resources into developing biometric data and exposure data in something called the US EPA Exposure Factors Handbook. At the link here noted on the slide will also be listed in the lecture notes online. This EPA Exposure Factors Handbook gives a tremendous amount of valuable data to help us understand and model given scenarios. Sometimes we'll also follow with pre-existing data like the Exposure Factors Handbook. We may actually conduct a survey of the people that we are interested in estimating exposures on. We may actually conduct surveys. For example, we might ask people, how much fish do you eat per week? If we're interested, say, for example, in assessing exposure to organic mercury in seafood. We might conduct surveys. So the EPA Exposure Factors Handbook has some pre-existing secondary data on that, but I might go out and say, I'm going to actually conduct a survey on the people that may be exposed to the seafood and ask them things like, what kind of seafood are you eating? How frequently do you eat seafood? How much of it do you eat? And so on, because that may help me assess exposure as well. If I have enough resources, it's possible that I go out and I actually directly observe exposures in the field and document exposures. For example, I've participated in some exposure assessments where people are looking at registered pesticides and interested in knowing how often children, for example, playing outside may actually come in contact with pesticides, and they'll actually go out and observe children playing outside and record their potential exposures. This could also be recorded and so on. So many of these different techniques can be utilized to try to develop as accurate data as possible that's as representative as possible to be fed into these models to evaluate given scenarios. So that is very important for us because we want to have good input data so that we can have good outputs from our models. So to summarize modeling and scenario evaluation, modeling strategy is going to be driven by the purpose and the goals of your assessment. Many different models are available, and they oftentimes tend to be very mathematically intensive, but can provide estimates and predict exposures. Data needs and model inputs are crucial. We need to have good, valid data being input into our models for us to have good outputs. And models may need to account for not only the transport of contaminants into the environment, but also assess their transformation in the environments. If those chemicals get modified or metabolized in the environment, that can also be crucial for us to having an effective scenario evaluation utilizing models.